Lesson 6 demo. In this class, we see our first derivative formulas. Warning, many of these formulas are not intuitive. Notation. We'll see this notation formally in a few classes, but d over dx and then brackets means the derivative of what's in the brackets. In the same way that you know that if you see this symbol, then you take the square root of whatever is inside of that symbol. So brand new symbol for us here, d over dx and then parentheses means take the derivative of what's in the brackets. Okay, in the last group activity, we proved that the derivative, this is our new notation, the derivative of the square root of x is 1 over 2 square root of x. We did that by doing a big old calculation. We had our difference quotient with a limit in the front. Then the technique was to rationalize. In this case, we had to multiply by square root of x plus h plus square root of x over itself. Then we distributed on the top, but not on the bottom, and we got this. The x is canceled, we were left with an h. The h is canceled, we were left with a 1 over. Then finally, we replaced h with 0. Didn't have to write the limit anymore, and got to 1 over 2 square root of x. In this class, we will see how to calculate certain derivatives very quickly. So we actually saw the shortcut for this last class as well. With the power rule, we'll see it more formally today. Number 1, if c is a constant, then the derivative of c is 0. That is, the derivative of any constant is 0. Makes sense, hopefully. If you think about the graph of y equals a constant, you should be imagining a horizontal line, and the derivative of any horizontal line is 0 everywhere. So for example, in number 2, the derivative of -7 is 0. The power rule, this is what we saw last class unofficially. The derivative of x to the n is n times x to the n minus 1. I like thinking about these rules in English as opposed to symbols. So in English, it says you bring the power down. The power is called n. You bring it down. You copy the x, there it is, and then you subtract 1 from the power. So n becomes 1 less. Subtract 1 from the power. So number 4 says the derivative of x to the 6th. So we bring the 6 down, we copy the x, we subtract 1 from the power, 6x to the 5th. That's it. Consider doing the difference quotient limit definition of the derivative on this problem, and you will see how much nicer this power rule is than that. The derivative of x to the -4, bring the power down, copy the x, subtract 1 from the power. Be very careful when the power is negative. Sometimes we go the wrong way. Subtracting 1 here gives -5, not -3. Okay, this next one we actually did last class unofficially, but we'll do it again here. In order to use the power rule, we need to write this as x to a power. So that's x to the 1/2. And then we do our power rule. Bring the power down, copy the x, subtract 1 from the power. That's it. You can do some algebra on this one to make it look like 1 over 2 square root of x. That's the answer from up above, but it's fine in its current form anyway. Okay, number 5. If c is a constant, then the derivative of c times f of x is equal to c times f of x. What that means is that a constant multiple can come outside of the derivative and get multiplied after you take the derivative. We do have 2 special cases over there. Let's look at them in just a second. First, we'll try the first one in number 6. Derivative of -2x to the 5th. So what the rule is that we just said, we just looked at. It says that this constant multiple -2 can come outside and can just hang out there until you take the derivative and then can be multiplied at the end. So the -2 is waiting. The derivative of x to the 5th, that's now easy. That's our power rule. 5 comes down. Copy the x, subtract 1, makes it 4. And then the -2 multiplies by that. All we can do is make it -10x to the 4th. And that's it. Now, I don't think I'm probably going to write this one out in as much detail anytime in the future this semester. So as a little shortcut here, the 5 comes down and multiplies by that -2. So the -2 is just hanging out, waiting for you to do the derivative. And we know the 5 comes down. And that's the multiplication that gets us the -10. Okay, let's take a look at the first special case. It says, let's actually take a look at the second special case. It says the derivative of any constant times x is the constant. So first, according to our new rule here, constant multiples can come outside. And so the constant c comes outside and waits for you to take a derivative of x. But if you think about the graph of y equals x, that's the thing in the brackets. Y equals x, again, is our 45-degree line going through the first quadrant. in the third quadrant. And the slope of that tangent line is the line itself for any place on y equals x. And the slope of that 45-degree line is 1. And so this just becomes c times 1, or c, which makes an awful lot of sense because actually the graph of y equals c to the x is also a straight line, and the slope of that straight line is c, and so that's what the derivative is. So coming down here to c, derivative of negative 24x is negative 24. That's it. That is all. You are welcome to do the power rule on this one. I'll show it to you one time. Negative 24 can come outside. Copy the x right there. Negative 24, waiting around. All right, there's an invisible first power on this x. The 1 comes down. Copy the x, subtract 1 from the power. X to the 0 is always 1. And so we get negative 24 as we expected. Okay, and then the last special case is this middle thing here. It says if you have a function on the top and a constant on the bottom, then you can just leave that constant on the bottom and take your derivative on top as usual. So the derivative, the function that was up there stays up there, and you just copy the constant that's on the bottom. So I think this is a really useful one. We are going to see another option for dealing with quotients, taking derivatives of quotients. But I promise you this is better than that one. So if you can use this one, you should. Okay, so here we go. Fraction. I see a 7 in the bottom. That's a constant multiple. It's like a times 1/7, so it stays in the bottom. And then x to the 12th upstairs becomes its derivative. 12 comes down, copy the x, subtract 1. That's it. Okay, 7. If c is a constant, then the derivative of c over x is negative c over x squared. This is probably the first big surprise. If things were nice, then we would just say, okay, keep the c on the top and then take the derivative of whatever's on the bottom, and the derivative of x is just 1. But things are not so nice. The special case we talked about hinged on the fact that the constant was on the bottom and that there was a function sitting on top, not on the bottom. So anyway, it's okay with me if you don't quite believe this one right now. It's still true. Constant over x becomes negative the constant over x squared. It's a shortcut. I think it's worth memorizing. So the derivative of 3 over x is negative 3 over x squared. And the derivative of negative 5 over t, change the sign on top, 5 over t squared. If you don't want to memorize this rule, then you are forced to play the following game. So suppose that we did the 3 over x. So in order to use the power rule, we need to get this to look like x to a power. And so that x on the bottom is really an x to the negative 1 upstairs. Now we'll use our power rule. We'll do it a little bit shorter here. The 3 stays. Negative 1 comes down and multiplies by the 3. Copy the x, subtract 1 carefully. Negative 2 there. So that's a negative 3x to the negative 2. And let's go ahead and move that x to the negative 2 downstairs and make it x to the positive 2. And you can see negative 3 over x squared is what we said. I don't know about you, but I'd much rather use this shortcut. So I think it's worth memorizing as a special case. Okay, number 9, sum and difference rules. Okay, they look like a mess, but they're actually some of the nicest derivative rules you will meet. If you want to take a derivative of the sum of 2 functions, you can take the derivative of the first function and take the derivative of the second function completely separate, and then add up your 2 final answers at the end. Subtraction works just as nicely. Take a derivative of the first guy, derivative of the second guy, and subtract them when you're done. So in English, the derivative of a sum or difference is the sum or difference of the derivatives. Let's take a look at number 10. Let's find the derivative of this function, and then we'll find the equation of a tangent line at x equals negative 1. So good notation here, f prime of x equals. So what I see is a plus sign and a minus sign and a plus sign. And I'm really happy about that, because that allows me to copy those signs in exactly that order and do my 4 derivatives completely independently of each other. So let's take a look at the first one. Negative 5x to the 4th, negative 5 there, multiplies by the 4 comes down, copy the x, subtract 1 from the power. Let's do the 7x squared. Copy the 7. 2 comes down. Copy the x, subtract 1. You don't need to put it, but I'll highlight the fact that there's a 1 there. Negative 3x, this is one of our special cases. The derivative there is just the number, it's 3. I've already got the negative written down. And then finally, 2 to the third. So 3 comes down, copy the 2, subtract 1 from the power. And if you're nodding your head, you are wrong. That is not the derivative of 2 to the third. 2 to the third is what kind of a creature? 2 to the third is a constant. 2 to the third is just the number 8. And we know that the derivative of any constant is 0. So don't fall for the trap. Just because it has a power on it doesn't mean you can start using the power rule. Okay, so we'll clean this up just a tad. Negative 20x to the third plus 14x minus 3. That's our derivative. And that's the first part of this problem. Then it says find the equation of the tangent line at x equals negative 1. So in order to find the equation of a tangent line, we need two things. We need the slope and we need a point. Let's do the non-calculus thing first. I know that x equals 1 is what I'm focused on, and I want to find the y value. So we're just plugging x equals 1 into the original. Negative 5 times 1 to the 4 plus 7 times 1 squared minus 3 plus 2 to the third is just 8. Negative 5 plus 7 plus 5, I think it's 7. Okay, so that means that the coordinates of the point we're interested in are negative 1, comma 7. Negative 1, 7. And that does not look like it agrees with my picture. So what happened here? Did I lose a, let's say negative 1 plus negative 5 plus 7 minus 3 plus 8. Okay, I see the problem, and probably many of you do too. I said I wanted to do f of negative 1, but instead I did f of 1. And so actually the point that I found was 1 comma 7. And 1 comma 7 is perfectly reasonable, but it isn't the point that we want. I want this point up here. So let's fix that. Okay, negative 1 to the fourth, and then negative 1 squared, and then negative 3 times negative 1. That's the one that I goofed on. I goofed on all of them, but that's the only one that mattered. Okay, so that should have been negative 3 times negative 1, and then plus the 8. Okay, so that's still negative 5, plus a 7, that's 2, and then plus a 3 is 5, plus another 3, I think it's 13. I'm going with that. And that seems reasonable looking at this picture right here. So that means the coordinates of our point are negative 1, comma 13. And we said to find the equation of a line, we need two things, a point and a slope. Well, we just got the point, so now we need to find the slope. And to find the slope of any tangent line, we use the derivative. And so we're not plugging negative 1 to the original function this time, we're plugging it into the derivative. So negative 20 times negative 1 cubed plus 14 times negative 1 minus 3. So that looks like 20 minus 17, which is 3. So does that seem reasonable looking at the picture that the slope is 3 at this one spot here? Yeah, maybe. I mean, it looks kind of like steepish here, but notice that the axes are not, they're not equally spaced, I guess, right? The vertical one is smushed down. So yeah, I could buy a slope of 3. It's positive, it's uphill, but not too steep. Okay, all of the calculus in this problem is done. This is now a straight up algebra problem with a point and a slope. And so we'll do our standard y equals mx plus b stuff. We know that the slope is 3. So I copied everything else, but just made that one change. And then we're going to plug in the point. The coordinates are circled up there. 13 is the y. Negative 1 is the x. B is the thing we're about to find. 13 equals negative 3 plus b. So b is 16. So that means that the final equation of my line, my tangent line, is y equals 3x plus 16. And just because we have the benefit of a picture up on top, we can actually see if that 16 seems reasonable. I've got my tangent line drawn. Does it look like the tangent line might hit around 16 on the y-axis? Yeah, I could buy that. Okay, so make sure that you are clear that if it says to find the equation of a tangent line, that you don't just stop after you found the derivative. That's an important part of the calculation, but it is not the equation of the tangent line. For that, we need a point and a slope, and then the mx plus b calculation.